Let's keep going with Taylor series that aren't focused at 0 to get some more practice. Let's think about a Taylor approximation for cosine x at c equals negative pi over 2, which seems a little weird, but I'm actually going for a system here, and it'll be more clear in a little while. So I've decided on, let's do order 0 through 5. Let's start taking derivatives. So f 0th derivative is cosine, and then we have what? Negative sine x, and then negative cosine x, and then sine x, and then derivative of sine again is positive cosine, and then negative sine of x. And then let's do the derivative value at c equals negative pi over 2, which takes some thinking. It's not horrible, but let's see. It's the derivative value at c. So this would be cosine of minus pi over 2. It might actually help here to draw sine and cosine real quick. So we're all focused around negative pi over 2 here. And then, so that's cosine, and sine does this. So this is how I was thinking about them in my head as I was practicing the problem. So cosine of negative pi over 2 is 0, sine of negative pi over 2 is negative 1, but this is negative sine of negative pi over 2. So that'd be negative negative 1, which is positive 1. And then cosine is 0 there, so we'd get negative 0, which is 0. Sine of negative pi over 2, we said is negative 1. And then cosine of negative pi over 2 is 0. And negative sine negative pi over 2, we actually just did that up here. That's still negative negative 1 or positive 1. And then what's our polynomial term? Oh, we forgot to say this is 0. So we'll get a 0 here plus 1 times, and try to remember how to write the polynomial term formulas when we aren't focused at 0, when we're focused at c. So it's x minus c, but we would usually fill in the c value we're using here. So it would be minus pi over 2 plus 0 times x minus pi over 2 squared, because we're on the order 2 derivative, divided by 2 factorial. Really, I didn't have to write all that because it's just 0 times that, but it's good to practice, right? It's good to see the system. Then plus a negative 1 x minus pi over 2 cubed over 3 factorial plus 0 times, okay, this time we'll skip it, and then plus positive 1 times x minus pi over 2 to the 5th divided by 5 factorial, and then just add those up, and that's our polynomial. So that's our 5th order Taylor polynomial. Do you notice anything interesting about this compared to the Taylor polynomial we got for just plain cosine? Do you remember we said the cosine polynomial, so cosine x at c equals 0, had even symmetry. It had zeros for all the odd power coefficients. But here we seem to have the exact opposite, right? Here's an odd power coefficient that has a non-zero. here's an odd power coefficient, odd power term that has a non-zero coefficient. In fact, it's the even power coefficients that have that are 0. So that's a little bit confusing. And it has non-zero for the odd power coefficients. But would you say that cosine has odd symmetry? That doesn't sound right. We know cosine has even symmetry. Well, let's go graph what's going on. So we've got our cosine here. We've defined our c as negative pi over 2, like we said. And I put a dot here saying where we're focusing around. And here's our 0th order approximation, which most people would say doesn't look all that good, but if you didn't know the function value was 0 there, you might really appreciate the hint that the function value is near 0 there, right? If you thought it might be 10 or 20 or 50 or negative 9 million or something. So that 0th order approximation does actually give us some information. Then here's the 1st order approximation. That's looking pretty good. That's our tangent line, right? And then let's do our 2nd order approximation, same as the first, because the 2nd order has a coefficient of 0 there. And then our 3rd order approximation is looking pretty good, better than the straight line. And our 4th order is the same as the 3rd order. And then 5th order stays on that cosine curve, or I mean really close to it visually, even farther than our 3rd and 4th order did. So that's making a fair bit of sense. So it looks like we did our calculations correctly. What about that thing about odd symmetry versus even symmetry? Well, we said cosine, let's turn these off. Cosine itself has even symmetry. It's symmetric left-right across the y-axis. But we're focused over here, and so if we kind of zoom in there and think of kind of that point as where everything is focused, almost like the y-axis, then this has odd symmetry. And all of our approximations, 1st order, 3rd order, 5th order, those all have odd symmetry. So it kind of makes sense. And in fact, what we're seeing is if this is like the y-axis, then this is almost more like sine than cosine, right? If I ignore this dark line here and think of this is almost my origin, then this is acting more like sine than cosine, and sine has odd symmetry, and all my functions, all my approximations have odd symmetry. So it actually does make sense, and there's some kind of system to it. Amazing.